All right.
Some of the last two minus some of the first one.
It has to be. You have to make full plays.
Basically, because they're all separated by one. Like you can find the end. I have no idea how to do the divisor.
Did you do the
I just did one. That was after the linear.
All right. So
I did number.
So last time we talked about wanting to use the fundamental theorem of calculus, but being unable to do so. So we're trying to solve this problem. What we'd really like to be able to say is that if I have some contour C, which say is just some circle centered at 0, centered. That's not how you say centered. What are we doing? Centered at z equals 0, radius r. We really wanted to be able to say that I should be able to use the fundamental theorem here. I mean, why not? Why shouldn't I just be able to choose that point right there and go in a circle and integrate this thing around the circle? If we did it with the parametric version of it, it came out to be 2 pi I, right? If we did the direct parametric substitution and we calculated this integral around that circle, we got 2 pi I. So we know what the answer is supposed to be. And so the rest of this class basically is going to be clever manipulations of contour integrals so that we can apply ideas of analytic functions. We're going to be doing a lot of that. So what we did last time was, I should remind you first what the fundamental theorem says. The fundamental theorem says that if you have a simply connected domain, I shouldn't write it like that, simply connected U, and a contour C that lives inside of U, and F analytic on U, I should say C is a simple closed curve, simple enclosed.
Is that like C? Does that say C is a subset of U or is an element of U?
It's a subset.
Okay.
Right. So it's a simple closed C contained inside of the domain U. So basically, the picture here is I have some domain U. I have some simple closed contour C living inside there. So there's C. F is analytic on the whole thing. Then the integral of F over the contour, actually, it was any contour, right? It was like this, from A to B. So not even simple closed, just piecewise smooth was the condition. Getting ahead of myself. It was piecewise and smooth. Then if you have the contour going from A to B, what the fundamental theorem said is that the integral of f dz on that contour was equal to capital F of B minus capital F of A. And the obstruction to using this in many cases is the fact that F may not be analytic and the domain might not be simply connected. Right? And so I really want to use the fundamental theorem of calculus to compute this problem, but I can't do it because while F does have an analytic antiderivative, it's not the case that I can take a contour through this line because log z is not analytic here. So log z fails to be analytic on this set. And so this is not even a sensible thing to write down for f of z, right? Like f of z is not analytic, so why would I not allowed to do this? And so the trick that I pointed out last time was we're not going to calculate this contour. We're going to calculate when we can use the fundamental theorem of calculus on, and then we're going to take its limit. So this is going to be a mixture of an integral we can compute, and then we're going to take a limit when we're finished. So the setup that we had last time was we're going to pick a point out here, which I'll call r e to the I pi minus 1 over n. So it's slightly less than the point that sits with argument pi, right? So this angle right here is pi minus 1 over n. And then I'm going to have this contour start at this point right here. This angle is going to be minus pi plus 1 over n. And so I have a point out here, r e to the I minus pi plus 1 over n. I'm going to call this point A, and I'm going to call that point B. and I'm going to integrate around the circle that attaches those things. Now, the reason that we do this is because the antiderivative of 1 over z is log z, and log z is not analytic on that purple set. So I can't use the fundamental theorem on any set that involves that purple set because log z is not analytic there. The argument has a branch cut inside of it. And so the claim is that everything about this picture is okay because this contour is contained in a simply connected domain. I can surround this contour with a simply connected domain on which 1 over z and log z are both analytic functions. Yep.
To be clear, the contour doesn't like sharply turn there. It's just you show.
No. I'm just this is not actually part of the contour.
Okay.
It's not part of it. Right. I was just trying to show you what the angles were. Right. Like the fact that I got the angles here. The contour that I'm going to integrate over is this contour, which we could even call Cn. For each 1 over n, there's a different contour. I can set it up like this, right? And on that contour, I can use the fundamental theorem of calculus because the function log z is analytic everywhere on this red set. And the contour lives inside the red set, and that says I'm allowed to apply the fundamental theorem of calculus, part A. So that means that the integral over Cn of 1 over z dz is equal to, well, the antiderivative of 1 over z is log z. And that's going to be evaluated from, I'm going to use the old calculus notation here, from A is equal to re to the I minus pi plus 1 over n to re to the I pi minus 1 over n, which is log re to the I pi minus 1 over n minus log re to the I minus pi plus 1 over n. That's all legit. I can do that. Everything was analytic and well-defined. I've stayed away from the branch cut of the argument. If I want to continue evaluating this, I have to remember that log of z is equal to the natural log of the length of z times, or plus I times the argument of z. But this is just r. It's the radius of the function. The radius in the polar representation. So the log of re to the I pi minus 1 over n, well, that is the radius. So this is the natural log of r plus I times the argument of that number, but this is the argument of that number, pi minus 1 over n. And likewise, here, the log of this number is the natural log of its radius plus I times its argument, so minus pi plus 1 over n. Just by the definition of the complex log. And it's not hard to see that these cancel. And this turns into I times 2 pi minus 2 over n. So that's not the integral I wanted. It's almost the integral I wanted. I want the integral where the circle comes in from both sides and touches up. I want this point and this point to come together so I get a calculation for the whole thing. How do you do that? Just let n go to infinity, right? If you let n go to infinity, that number is going to get smaller and smaller and smaller. These contours will get closer and closer. So in the limit as n goes to infinity of the integral of Cn of f of z dz is 2 pi I. So we can use the fundamental theorem of calculus or the fundamental theorem of complex functions, part A, to recover the thing that we got out of the contour integration, but we have to use some tricks to do it to make sure that I'm only integrating where the function is analytic. Okay? And this idea of avoiding singularities and avoiding branch cuts, that's really important. So one question that you might have is, well, what are we actually allowed to do? What calculus ideas do we actually have available? We learned all these rules in calculus. What can we do? And the answer is, if you go to your textbook and you look at, those of you who haven't looked at it in a while, if you want to look at it, other than the exercises, there's this table on page 107 where he tells you, like, all the antiderivatives that you already know are antiderivatives that you can continue to use. And all the basic rules of calculus, of integrations, still apply. You can use the U substitution. You can use, turns out you can use the integration by parts. In fact, I've assigned you an exercise that says prove the integration by parts formula. Because it's not like an epsilon delta proof, but it's amusing. So like the same rules of calculus that you know, you already can use as long as your setup is where a function is analytic. Okay. All right, so again, the point of all of this exercise was, this is what we need to do if we want to calculate an integral but not use the parameterization of the path. Oftentimes that's the worst way to do an integral. You can imagine if the function was more complicated than 1 over z, it might just be impossible to calculate the integral using the parameterization. Like r e to the I theta is running all over the place. Okay, so, we okay with this so far? Yep.
Artificially nastily constructed complex functions aside.
Yeah.
Is it generally true that this approach of cleverly defining your domain be simply connected, and then doing the limit trick will always
It's the
work?
general strategy we're going to use. In fact, it's one of the next thing, after we build up a theory of integration, what we're going to study is functions that are rational functions. And so the study of rational functions is the study of functions with asymptotes. So in that case, what you end up doing is a library of contours where you draw them carefully so you always go around where the asymptotes are. So yeah, this is going to continue. This idea of forcing the domain to be simply connected and forcing the function to be analytic and then taking limits is like the theme of complex analysis, at least the first quarter of it.
Cool.
You'll get lots of practice with this stuff, I promise. All right, questions about this? Yep.
What if I wanted to do a similar? What if I wanted to integrate? Is it possible to do an integral that's not the principal angle region?
Uh-huh.
So what if I wanted to integrate from B to A, going the other direction?
Yeah. So implicitly here, implicitly in what I've done here is, as soon as I calculate, an antiderivative of 1 over z is log z, but like you have to select a branch of the log before you get started with that. Every time you use the logarithm at all, you are automatically choosing implicitly a range of angles that it's going to take on. Okay. Right? So like that's part of the choice that you're making when you set this up. Other questions? All right. Okay, so let's go on to maybe the most, the beginning theorem of all of the rest of complex analysis, which is called Cauchy's theorem. I mean, everything is called Cauchy's theorem, but this is the first theorem called Cauchy's theorem. It doesn't help that Cauchy did so much math in so many different areas of math that even in individual areas of math, there's a Cauchy's theorem for groups. But this is Cauchy's famous theorem, sometimes called Cauchy's integral theorem. So, Cauchy's theorem. Now, some of you probably have already anticipated what Cauchy's theorem says. So, I'm going to write down a statement. I want you to tell me why you think it might be true. So, without setting any conditions at all, I'm just going to say assume f is nice enough so that f is analytic. So, f of z is equal to the sum from n equals 0 to infinity of an z minus a to the n. For some coefficients in some center, we have f, convergent power series. What should this be? What should you believe this should be? The integral around a simple closed curve C of f of z dz. 0. Why should it be 0?
Starting and ending in the same place.
So, I mean, what we want to do is we want to formalize, but we don't actually know that yet. We've guessed that that's the case, right? What we've shown is equal to 0 at this point. But which integrals we've shown are 0? We showed that if you integrated z to the n dz around a simple closed curve and n was bigger than or equal to 0, n was some integer larger than -1, we showed that this integral was equal to 0, where c is any simple closed curve. Well, we didn't, where c is some circle. C, a circle. We showed that that was true by just directly doing the parameterization and plugging it in and seeing that you subtract 1 from itself and you get 0 out the other side. So we showed that's true. Why should I believe that's true? Yep.
You can find an antiderivative of z if you just integrate term by term.
I want a better, so that's true, but we haven't, so the fact that analytic functions have antiderivatives turns out to be a consequence of Cauchy's theorem, not a way that you prove it. I want the intuition behind why I'm going to assert this is equal to 0 for C, a circle. And I want to know why. The intuitive version of why. Because with complex analysis, a lot of these ideas have really clear intuitions about why they might be true that aren't proofs, but they lead you to what the theorems should be, and they help you understand why the theorems are true. What if I took that integral and I replaced f with its power series?
Each individual term would be 0.
All of these guys are z to the n's, right? This is an integral of z to the n. Each individual term here is z to the n, basically. So when we're integrating z to the n, I mean, okay, here's where the first intuitive move that's not really allowed, but we're going to do it anyway. Because this is an intuitive argument, right? Intuitive arguments, you're allowed to say, okay, if this was true, if it was true that I could swap the integral and the sum, if that was a true thing I could do, then you would have this. The an would pop out, and I would have individual integrals that look like z minus a to the n over those circles. But each individual one of these is just this guy. You could do it with a direct parameterization, and you would get 1 minus 1, which would be equal to 0 for each term. So if you could do this, if you could take a power series and swap the integral and sum, it would be obvious from that computation, which we did directly, that this is a sum of zeros, and so is equal to 0. Now this is a function, not a value, right? So this is the 0 function that we're asserting that this thing is equal to now. But the idea is, if I integrated this naively, looking for an antiderivative around some closed curve, actually this is a value because we're doing over a contour here, you put in the beginning point and the end point, they're the same. You know, whatever's going on, you calculate this term by term and you get 0. That's why you should believe this is true, right? In complex analysis, if you want to know why a theorem is true, put in a power series and see if you can pull out why it's true from the power series. Power series would give you all the intuition about what's happening. So this is the way I think about it anyway. If I integrated a polynomial, it would be obvious this was true because sums and integrals definitely switch for polynomials. So if we could also switch these guys for power series because we knew something about absolute and uniform convergence, I could just do this. All right, is it clear? How, I mean, is what's going on, what I'm trying to do here clear? It would be easier maybe, I could even take the minus a's out if those are confusing people. Just do the whole thing, take out the minus a's, it's the same question, right? Okay, so how do we actually have to prove it, though? Because we don't get to do this. We have no justification for doing this, so we've got to do it a different way. Yeah.
To be clear, your curve C is a circle centered at A.
It's a circle
When the
centered,
A's
yeah.
were
This is a
okay.
circle
Okay.
centered at, in this case, z is equal to 0, but the way I had it written before, z is equal to a. That's right. That's the way we did it before, so that everything canceled and we ended up with this radius thing. Okay. So this is where I get to make the sort of like wind out of the sails assertion that essentially all of complex analysis is a consequence of Green's theorem. So let's actually prove Cauchy's theorem. So this is what it looks like with all of its hypotheses. And I'm going to put Gorsah is the guy who actually proved it in its full generality. I'm going to make a big assumption in the proof of this that is not, that doesn't prove the full case, and there's two different ways of fixing it, and one is due to Gorsah. Okay, so let F be analytic on a simply connected domain. U. And let's let C be a piecewise, smooth, simple. You know, math class is getting good when objects get 5 or 6 adjectives, right? Piecewise, smooth, simple, closed curve in U. then the integral of f around C is 0. So that's the precise set of conditions that we need here. So we're going to do an argument that does not use anything about power series. It's going to run through Green's theorem instead. And that means I get to ask people, who remembers the statement of Green's theorem? Some of you were my students 3 months ago. Here, I'll give you the first half of it, and you tell me the conclusion. All right, so here's a C. Right? There's a contour, and it's wrapped around some region R, say. Right? Here's the first statement in Green's theorem. The integral of m dx plus n dy from A to B, or rather, we don't even have to parameterize, let's just say around the contour, is equal to?
0.
No! Only if it's an exact sort of conservative vector field, yep.
The integral over the region bounded by C.
The double integral over the region, because it's an area integral, right? Green's theorem is a way of getting from contour integrals to area integrals, right? It's a way of relating single variable objects to two variable objects. You go back and forth from contour integrals to area integrals. And what goes in the middle, though? See, that's the problem, is what goes in the middle.
The partial of m with respect to x.
Yep.
Minus the partial of m with respect to y.
Okay, so this is Green's theorem. What sort of assumptions do you need to make about m and n? See, now I'm gonna push. How about m and n? What do I need to know?
C1.
There's C1. Ah, that's always a good guess, right? M and n are C1. So if m and n are class C1, you can use Green's theorem. And what Green's theorem shows up all the time in all kinds of contexts, because sometimes it's really crappy to use a parameterized function to calculate an integral, and it's much easier to do it with an area integral. And sometimes area integrals are awful, and it's much better to work on the boundary instead, right? Green's theorem is a way of going back and forth between these sort of differential forms on the boundary to this sort of object on the surface. Now, this condition right here, this is famous, right? Yep.
Good question. So M and M are the like one-dimensional parameterizations of the curve.
They're
break it into
actually
components,
components of a vector field,
Right.
but evaluated on the parameter on just over C, right?
Okay.
So we assume here that we have some sort of the way that you evaluate this is you parameterize C and you plug it into M, N, and also dx and dy. So C will typically be parameterized with something like gamma of t, and then this turns into the integral of m of x of t, y of t times x prime of t dt plus n, I can't believe I'm writing this out, n of x of t, y of, it matters because I'm going to use an expression like this later, right? N of x and t, y of t, y prime of t dt. This is typically how this goes, right? You start with this object, you come up with a parameterization of the curve, and you just plug everything in, and you get some monstrosity like this out the other side. That should at least look familiar to you. You know, you've definitely, oh, I should say, not you've definitely seen it. You were supposed to have seen it in your Calculus 4 class. Supposed to. Which does not mean that you did, but you're supposed to have seen that this is actually one of the goals of the class, is to get you here. Okay. This thing being equal to 0 means that the integral is equal to 0. And this has many names. If you have a vector field with components m and n, and this condition is equal to 0, then it's called a conservative vector field, because these integrals are always 0. Or, if you take a differential equations class, this is what characterizes exact equations from differential equations and tells you when there's a potential function that sits on top of the m and n. So this is an incredibly important equation. It's also going to turn out to be equivalent to the Cauchy-Riemann equations in complex analysis. Okay, so we're going to save that off to the side. There's Green's theorem just waiting to be invoked. Okay, so let's let R be the region inside the contour C. then the integral around c of f of z dz. Okay, if I picked a parameterization of the curve, that means I could write this as the integral from a to b of u of x and y plus I v of x and y. So I write f in terms of its real and imaginary part. And then dz, that's x prime of t plus I times y prime of t dt. This is where z of t is equal to x of t plus I times y of t. It's a standard presentation of a parameterized function, right? You choose a parameterization of the curve, z of t, you plug everything in, and this is actually how you evaluate one of these integrals. We've done this a couple of times already. So now I'm just going to multiply some crap out. Yep.
What is that, let R be, what is that word?
Region. Let R be
Okay.
the region inside this contour C. So it's this picture. I've got some contour C, and I have some region R, it's the region bounded by C. Because to use Green, I'm setting up to use Green's theorem, basically, is what's happening here. Okay, now if you multiply this out, because that's what you do in a class when you don't know what else to do, is you just multiply some things out. You're going to end up with the integral from a to b of, okay, so the u is going to hit this x prime, so you're going to have a u and an x prime and a dt. And then the other real part is going to be this iv that hits this y prime. So there's going to be a minus v y prime dt. Hey, no laughing yet. Even if you already see where this is going. Okay, that's the stuff that was real, right? The u hit the x prime, and the iv hit the iy, which turns into a -1, and this falls out. Then you have an I, and then what comes out when you do that? There's IV x prime, Vx prime dt, and then there's a, what's the other imaginary chunk here? Vx prime, I did Vx prime, oh, U I y prime, right? U y prime dt. Now, if you remember your multivariable calculus, every time I write x prime dt, that's dx. That's the definition of the differential of dx. So this is really the integral of ab of u dx minus v dy plus I times the integral from a to b of v dx plus u dy. Boy, oh boy. This, by the way, the fact that we did this is we're building up to something called the complex version of Green's theorem. Those sure look like they're ripe to have Green's theorem applied to them. Right? I mean, I have the right sort of thing. There's m, and there's n, and there's m, and there's n. This is set up in the correct way, so now this is where I do the cop-out, and I make the assumption that's not really justified. I'll even give this an asterisk. Suppose that U and V are class C1. Now, I will point out this is a weakness in this approach because I'm proving a special case and not the full theorem. But there is a version of Green's theorem that holds when these are not class C1, when they're just continuous, which means this same structure will prove the argument in general. Okay? If U and V are of class C1, I can apply Green's theorem. All right. So what does the first integral turn into? Well, the m is the thing that stuck to the dx, and the n is the thing that stuck to the dy. So that first integral is going to turn into, so if this is integral 1, it turns into integral 1 over here, which is the double integral over r of minus dv dx minus du dy. And I can be even lazy and write dA there, since it's a region integral. It's dx dy, but I said dA. That integral turns into this one by Green's theorem. Right? M was equal to u, n was equal to minus v. And so an application of Green's theorem to the real part gets you this. Plus I times the double integral over r of, okay, so in this one, m is equal to v and n is equal to u. So we get du dx minus dv dy Yeah, and I bet if you look really closely, you can tell me what those integrals evaluate to. Because at the very beginning of all of this, we assumed f was analytic. Remind me what the Cauchy-Riemann equations are? Ux is equal to Vy, oh, okay. Well, if Ux is equal to Vy, then that's 0. What's the other Cauchy-Riemann equation? Negative V x is equal to Uy, oh, well that means this is equal to 0.
Whoa.
Yeah. Real impressive, right? There we go. Complex analysis is consequence of Green's theorem. Yep.
Why do you have to change the double integral if it satisfies the
It doesn't, because these aren't partial derivatives, right? This is the different. This is like you think of this as a vector field, right? This is a vector field with components u and v that we've expressed in its differential form. This is not a vector field. This is pulling the vector field back to a scalar valued function built out of the pieces of u and v, right? And so the Cauchy-Riemann equations basically force all of this to be equal to 0, and so you're done, right? That's it. By Green's theorem, this was equal to the original. All this nonsense was just to say this whole thing is equal to 0. So a couple things I want you to notice about this, which is when I keep saying that there's a deep connection between analytic functions and conservative vector fields, this is what I mean, right? Analytic functions are built out of pieces that are conservative vector fields. And this is part of the reason, I mean, it should be, if you've seen this stuff enough in conservative vector fields, you should buy that that's why these closed loop integrals are nothing, right? Essentially, you're asserting something about the behavior of the pieces of f, and that is that the pieces of f essentially are conservative vector fields. There's an extra chapter in the book that talks about how you would actually express this in terms of differential geometry. But yeah, that's it. Now what Gaursat did, just to let you know kind of what Gaursat's argument, if you really want to know the hard version of this, that does not have the assumption that u and v are class C1, then one book that you can look at, well, you can look in the big Rudin functional analysis book, or real and complex analysis book, which is a gnarly proof. You can look in the Marsden complex analysis text, and what he does is say, okay, so what the Gaursat version of the theorem is the same kind of argument. And if you know the proof of Green's theorem, what it does is it chops the region up into rectangles, and then it builds an orientation through the rectangles that's consistent so that you're rotating around the rectangles in sort of a circulation way. It's the same proof, actually, about like the divergence theorem or the curl theorem from vector calculus. So you you sort of subdivide and subdivide and subdivide, and if you can prove it on all the rectangles that it's 0 in every rectangle, then you can add them all together and you get that it's 0 everywhere. So it's a long, involved proof. I think it takes 8 lemmas in the Marsden text to prove it all the way. What I want you to think is, essentially what's going on here is, if you make the assumption these are class C1, which is a reasonable assumption for analytic functions, and this is the version that Cauchy himself proved, that it's a consequence of Green's theorem that Cauchy's theorem holds. Analytic functions integrate to 0 on simply connected domains, on closed contours and simply connected domains. And that means that we're set up for maybe my favorite cheesy theorem in this section of the book. Yep?
The one with the little rectangles, that one used Green's theorem on like a little
It uses Green's theorem on the pieces. You have to be careful. Essentially, it's a reduction to Green's theorem, right? So there's a couple of different ways to go, but yeah, you cut it down to rectangles, and then, I mean, that's how those sort of proofs work. You chop it down to little rectangles, you throw away the bad rectangles, and you argue they're very small, and then you just use Green's theorem on the rest of it. Okay, so, see that? One reason to do an argument like this is to try to convince you that you spend your life thinking that math is built out of these compartmentalized boxes, and there's this kind, and there's this kind, and there's this kind. But from the perspective of somebody who does this, it's all the same thing. Complex analysis and vector analysis and real analysis and functional analysis and algebra, or basically linear algebra, are all the same thing. They just flow into each other. There's not hard lines. In fact, we're going to see as we go on that there's going to be connections with other fields of math, like pretty surprising ones. Okay. So now we get to prove a result called the circle contour theorem, which basically says any contour integral reduces to an integral around a circle. Which probably seems pretty believable, but the argument is so funny that I feel like it's amusing to do the argument. So, what we have now, let's do an example. I like examples. Let's integrate the cosine of z dz over some contour C, where C is the set where, let's see, C is equal to the set of all z's so that the absolute value of z is equal to 3. Okay, you guys ready? This is going to be a heavy computation. Cosine of z is analytic everywhere, and since C is a simple closed curve, the Cauchy-Goursat theorem applies, and so this is equal to 0. The end. These are the kind of examples you live for. Okay, if you don't follow what's going on here, cosine of z is analytic everywhere. And so, and the circle, C, is a simple, closed, piecewise smooth contour. And so we've met the conditions to apply the Cauchy-Goursat theorem, so we invoke it. To imply, I mean, this is basically all you need to do if you want to apply Cauchy-Goursat, is to notice that a function is analytic, that on some set, that the contour that you're integrating around is a closed, simple contour inside that set where the function is analytic, and so therefore the function is 0. There's actually an even easier way of writing all this nonsense. So there's a phrase that covers all of this, the analytic everywhere, and simple closed, piecewise smooth contour, because who wants to write that over and over again? What you say is, f is analytic inside and across the contour of C. And what you mean by that, whenever you say that, what you mean is that if you have a contour, that you can find a simply connected domain that completely surrounds the contour on which the function is analytic. So to say that f is analytic inside and across the contour is to say that I can find some domain U, which is simply connected, on which f is analytic. So the book will invoke that a lot of times, so it doesn't have to write 9,000 words to describe what's going on with analyticity. A piecewise smooth contour on which f is analytic inside and across the contour. So this is the phrase. Analytic inside and across. So analytic on the contour, and we can put a little bubble around it where the function is still analytic. All right, so I got one more theorem to go here. Maybe I should do a real example first. Maybe we'll do it, instead of doing the circle contour theorem, we'll do an actual example. Let's do this one. Otherwise, it's just nothing but theory, which is my favorite, but people like examples. I like examples. How about the integral of the function 2z over z squared plus 4 dz over a circle C, where C is that same circle. C is the set of all z's that have modulus 3. Now, you probably don't want to do that parametrically, because nothing is going to cancel in a nice way, right? You're going to have e to the it's that are squared down here, but then this plus 4 gets in the way, and there's an e to the it up here, and another e to the it over here, and it's not actually going to be clear how to integrate the thing that you get out the other side. Just piles of exponentials running over the place. So the trick is, whenever we can get away with not using parametric integrals, we should. So I would love to be able to use previous results here. Does the Cauchy-Goursat theorem apply?
No.
Why not?
2i.
Because this thing has, it's not analytic, right? So this one, you say, okay, well, where does this have pole? Where? Sorry, I used a word you don't know yet. Where does this have asymptotes? Asymptotes is we'll have to replace this word at some point. Asymptotes. And the answer is whenever z squared plus 4 is equal to 0. Where is z squared plus 4 equal to 0? Somebody said one of the places where it happens, 2i, and negative 2i. This function actually factors as 2z over z plus 2i times z minus 2i. And so this is not defined at z is equal to 2i or z is equal to minus 2i. I have some circle, but I've got places where the function is not defined, and so there's no way it could be analytic. It's not even defined there, right? So I can't say it's equal to 0. Damn. Maybe I can make it into simpler functions. If only there was a technique that I could use to turn a rational function into smaller rational functions that I could get a handle on. A technique that your professors have been telling you you're not allowed to forget for your entire mathematical careers, or engineering careers, or physics careers. A technique that you can use to chop things into rational pieces. You didn't think you were going to escape partial fractions just because we were in complex analysis, did you? In fact, we're going to be doing partial fractions over and over again. So, the same exact rules that you learned for partial fractions way back when your professor very clearly walked you thoroughly through the theory of partial fractions, except we can throw away all the stuff that sucks because there's no irreducible quadratics anymore. So, 2z, yeah, I mean, ax plus b type terms. 2z over z plus 2i times z minus 2i is equal to a over z plus 2i plus b over z. Somebody worked really hard to make this problem nice. Now, I don't know what your favorite method for solving partial fractions is. I like the one where you mystify first-year students by covering terms up and plugging numbers in and then just pulling them out of thin air. like where you go like this. Well, let's see. It must be 1. Or I can mystify you guys, too. Oh, let's see. Oh, it must be minus 1. There, I did it. Or I could say, another way of doing this is 2z is equal to a times z minus 2i plus b times z plus 2i, and then just choose good values of z to cancel terms out, right? The same trick works here. So if you plug in z is equal to 2i, you end up with 2 times 2i is equal to a times 0 plus b times 4i, and so b is equal to 1. And if you choose to plug in minus 2i, then you get out minus 4i is equal to a times, are they both 1? Wow, I didn't even do it right. Plus 0, so a is equal to 1? Okay, fair enough. If you don't remember partial fractions, I would recommend that it might be a good idea to go back and look at them again. Okay, so now that you've done that, no sighing. You don't even know what rational functions are going to look like in this class. This is why Wolfram Alpha exists. You can just ask it to do a partial fraction decomposition for you. Yes. Okay, so our integral around this circle C of 2z over z squared plus 4 dz can be rewritten as an integral around C of 1 over z plus 2i dz plus an integral around C of 1 over z minus 2i dz. And now we just have to figure out, okay, so we've broken it into 2 integrals now. We've got our 2i and our minus 2i. Now the problem is we're still not analytic. But if it turns out to be the case, and this is a theorem I haven't proved yet, but I want to motivate it for next time. If it turns out to be the case that the integral of a function around any contour can be reduced to a circle inside there, if I can replace, imagine, I want to integrate this thing with reference to that pole right there. Pole, asymptote, singularity, whatever. What we showed before is that if I had a circle just around that that was minus 2i plus r e to the it, that turns into 2 pi I. That specific circle, if I parameterized it and plugged it in, this would be equal to 2 pi I. On this circle, where that's equal to 2i plus r e to the it, this function would be equal to 2 pi I. Because this function doesn't see that asymptote, and this function doesn't see, this function doesn't see this number, and this function doesn't see an asymptote here, right? They each just have one thing. So if we could do this, if we could say integrating around this circle is the same as integrating around that one, or integrating around this circle for this function, integrating around this circle is the same as integrating around that one, and for this function, integrating around the big circle is the same as integrating around that one. If that was true, this would be 4 pi I. So the aptly named circle contour theorem says, circle contour theorem says the following. If, loosely, if C1 is inside C2, and F is analytic, inside, I would say that, analytic on a simply connected domain containing both, then the integral around C1 of F is equal to the integral around C2 of F. I'm allowed to replace contours.
Would F be analytic on a simply connected domain containing full circles in this case, though?
What do you mean?
Because it's not analytic.
Oh yeah, I lied to you actually. I lied. I missed something here in the hypotheses. What am I stated theorem without knowing the one interior outline of domain U that contains the curves? Yeah. Okay. So I'm gonna there's a trick here basically. I'm gonna assert that there's a trick. So F is not analytic on this. F is certainly not analytic here, and this neither one of these is analytic on this set either, right? Okay. So we're going to use the circle contour theorem to assert that I can make moves like this, that I can break functions up, and I can say, like, whatever the value of the function was on this big curve, it's the same as if I reduced it to a circle. Because where's the bad behavior? If this wasn't here, it would integrate to 0, right? So any set that contains that singular point, any curve that contains it, should still carry the information that that singularity lives inside. That's the intuition here. If that wasn't there, the function would be 0. This integral would be 0. There's integral on a closed curve. So any contour that contains that singularity should encode the fact that that singularity is there when I integrate around it, no matter what shape it is. Okay, so I could try to rip out some proof of this real quick, but I want to talk about this next time. So the idea is we're stuck here. I use partial fractions. I want to divide this up and say that these things are both equal to 2 pi I. But I somehow need to be able to say that the integral on this is equal to the integral on that for this function. And the integral on this is equal to the integral on that for this function. So if I could do that, then I would have the result that I want. So that's what we're going to look at next time is, well, I guess next time is homework day, but this is what I want to talk about is the circle contour theorem, and then we're going to lift that into what's called the Cauchy integral theorem. Yep?
Why do you have to do partial fractions? You already know how to have those are plus or minus 2i.
Well, I mean, so the thing is because we've already computed what this is on those little circles, right? We did it directly. So we already know the value of this integral on that circle, and we know the value of this integral on this one directly. Generally, you don't. Generally, there's going to be a method that says, how many singularities are inside the contour, count them, and then multiply by 2 pi I, right? That's definitely a thing that we're going to be doing, but not yet.